Well, welcome back. We're actually going to continue with some substitution. Now, I did actually, at the end of last time, some substitution. Now, for the people in this room, last time was last semester, and it was actually a different course. And at Princeton Math 104, which is what we're now in, says that we're going to do substitution again. So for those watching online, you may find there is some duplication in the first half hour. But for the rest of the lecture, I'd like to continue with integration by parts. And then I'm going to skip a little bit and talk about some trigonometric integrals. And this is an interesting thing because actually in Math 104, for those of you in the room, this is not really covered explicitly as a topic, and yet you're still supposed to know how to do these integrals. So I thought I would show you a bunch of integration techniques involving trig integrals as well. So that's the agenda for today. So let's go back over and talk about substitution. By the way, even though we're being videoed, questions are encouraged. I wish I could answer yours out on the web, but it's not possible. So please, if you do have any questions, feel free to ask. Okay, so working in chapter 18 of my book, Calculus Lifesaver, section 18.1, here's the deal. Suppose you'd like to differentiate e to the x squared. What do? Chain it. The derivative of e to the something is just e to the same thing, but you have to compensate by multiplying by the derivative of that thing. Okay, well, if we want to turn this around and express it as an integral, we can integrate the right-hand side and say that the antiderivatives of 2x e to the x squared are e to the x squared plus a constant. Of course, if you differentiate the constant, you get 0. So that's great. So you'd think that it should be pretty simple to integrate e to the x squared. After all, e to the x squared is simpler than 2x e to the x squared, but you can't. There's no way to do this. Not really. You have to come up with some series or some sort of half-baked solution. You can get an approximate solution in terms of a definite integral, but there's no nice, simple, closed-form solution of this. And I'm not going to prove that. It's quite difficult to prove. But it's sort of surprising that the more complicated integral works. Why does it work? It works because the derivative of this nasty thing, x squared, is just sitting there as a factor. So what we're going to try to do is reverse the chain rule. And that's the method of substitution. By the way, somehow this method has become known as U substitution. But it doesn't have to be U. You can call it any letter you like. In fact, I like to use T because in about half an hour we're going to do integration by parts, and there you use U and V. Normal, U and V. And sometimes you have to do a problem with both substitution and integration by parts. Then you could get really confused if you do U and then U and V. You can't repeat the variables. So just call it substitution, and if you happen to choose U, you can call it U substitution. Yes, a question?
Why do the x squared equal e to the x squared
over 2x? Good question. Why does this integral not equal e to the x squared over 2x? I'm going to put question marks there because it's not true. In fact, all you have to do is differentiate this. You'll have to use the quotient rule, and you'll get something quite different. In fact, you should try it. You'll get, 2x times the derivative of this minus. It's going to be a much more complicated expression that may simplify, but it certainly doesn't simplify to this. Try it and see.
Well, will we know when to use this method?
Well, the question is, when do we use this method and when do we use substitution? Well, that's what I'm going to talk about. Okay? So, actually, I should just introduce this whole suite of topics. For the next 3 lectures, review sessions, 3 weeks in this course, we're going to be doing techniques of integration. What this means is, here's an integral, work it out. What techniques? It's like building up a toolkit. I'm giving you tools, or we're giving you tools to evaluate integrals. And sometimes it's not clear exactly which tool to use. So what I'm going to do is show you substitution, then I'm going to show you integration by parts, and I will show you a few other techniques for trig powers. And the deal is that I'll try to say when you should use them, but at the end, in 2 weeks' time, not this one, not the next one, but the week after, or the lecture afterwards, I will do a summary of the techniques and try to show you how to decide which one. Okay? So we've got to see what the techniques are first before we can decide what to do. Now, as I was saying, to deal with this integral here, we notice that 2x seems to be the derivative of x squared. And so that might lead us to this solution. The question is, though, how can we see it? All I'm going to do is show you a way that you can sort of, without doing it in your head, just a few steps of working, arrive at such an answer. So, as I say, you've probably seen this before, certainly if you took Math 103. But confronted with this, I look at this and I say, we've got e to the something. It's not just e to the x. It's e to the something nasty, like x squared. So let's let t equal x squared. And I would like to move this integral over from x land to t land. I think of it as a sort of migration. Now, the thing is, you've got this dx, which is basically how x changes. And if you change x by a little bit, t does not change by the same amount. You need to change the dx over to t land as well. And you do this by differentiating in our working box over here. Now, if I wrote dt dx equals 2x, that would be fair enough. And by the chain rule, there's a bit of justification to be done. And if you're really interested, it is in section 18.1.3 of my book. I'm not going to do that tonight, but you can read over that at your own leisure if you like. It justifies this by the chain rule. But in any case, the point here is that this 2x and dx together can be replaced in t land by dt, and the e to the x squared becomes e to the t. So this whole expression in t land is integral of e to the t dt. And that's just a straightforward integral. We know this is e to the t plus a constant. Unfortunately, that's not the final answer. We have to go back to x land. See, we invented t. It's a fantasy variable, as it were. So we've got to get back. It's not a very exciting fantasy, I have to say, but, you know, we have to go back to x land. So we end up with e to the x squared plus c. All right. Let me give you another example. Consider the integral of x squared cosine of x cubed dx. All right. Again, it's not just cosine of x. It's cosine of something messy, x cubed. So let's set t equal x cubed. Not cosine of x cubed, just x cubed. It's the interior bit that's messy. And everything is beautiful because the derivative is 3x squared dx. Now, I might have anticipated this because we see the x squared dx. It's not 3x squared, but that's okay. The 3 is just a constant. In fact, we can divide and write that 1/3 dt is x squared dx. So if we take the x squared and the dx, we're going to replace that by 1/3. So we get cosine, x cubed is just t, and the rest of it, x squared dx, becomes 1/3 dx. And the third is pretty inoffensive. It just pops outside the integral. The integral of cosine is sine, not negative sine. That's a very common mistake. Careful. Just do a mental check. The derivative of sine is cosine, not minus cosine. So there's the answer in t land. Of course, we go back to x land by replacing t by x cubed. As I say, you can use u or v or theta or any variable that you like, and these things are correct. It would still be true, yeah. The top, right line. You're having, thank you. Is that what you were going to say as well? Thank you. Yes, I frequently make mistakes. Some of them silly like this, and sometimes more serious. If I make too many, I have been known to run away. But please do correct me. Well, hide behind the podium or something like that. This is all possible. But I appreciate the corrections. Good. Any other questions about this? All right, so these are fairly straightforward examples. Now, let's take a look at a certain class of examples. Okay, this one looks pretty messy. Integral of 3x squared plus 7 over x cubed plus 7x minus 9. Okay, looks pretty nasty, but there is, again, one saving grace, as it were. The derivative of the bottom is exactly what you have on top. Kind of lucky. Kind of lucky. If it's not, you have to use partial fractions. But that we will do next time. As it happens in this case, we can avoid that, as I said. If you just let t be the bottom, x cubed plus 7x minus 9, you find dt is 3x squared plus 7 dx. And hey, that's exactly what we have on the top. So this ends up becoming just 1 over t dt in t land. The entire top is dt, and the bottom is just t. So this time you get natural log of the absolute value of t plus a constant. And if you replace this, again, t, you get natural log absolute value of x cubed plus 7x minus 9 plus a constant. Now, this is a special case of a more general rule. Whenever you have a fraction where the numerator is the derivative of the denominator, the answer is just the log of the absolute value of the denominator. So, plus a constant. So in symbols, what this says is, if you have some denominator, call it f of x, and the top happens to be exactly the derivative, then the substitution t equals f of x is going to give you dt as f prime of x dx, and you will find that you just get the log of the absolute value of the bottom plus a constant. And that's sort of worth just memorizing, because you can actually save on a substitution. You kind of get used to these things, and you don't really even do a substitution. For example, suppose you have something like this. Dx over x log x. That sort of looks tricky, but actually the derivative of log x is 1 over x. So if you're really cunning, then you write it like this. This is sort of sneaky. The substitution t equals log x is what you need, but you can sort of save a step. Now I've written it as a function whose derivative, 1 over x, is sitting up in the numerator. And because the derivative is just up there, the answer is just the log of the bottom. With absolute values and a plus c. If you don't believe it, try setting instead t equals log x, so that dt is 1 over x dx. And again, in t land, you will find that you just get 1 over t dt, just like the top line there. But I'll leave that to you. I like this method, combined with that formula in the box up there. Kind of sneaky. Along the same sort of lines, here's a similar example. Suppose I ask you for the integral, let's do this. integral of dx over square root 1 minus x squared inverse sine x, also known as arc sine x. You could do a substitution, t equals inverse sine x. And again, it's worth just trying and convincing yourself that the other sneaky way to do it is exactly what we did before. Just bring that 1 over 1 minus x squared square root into the numerator. And now notice that the derivative of inverse sine is exactly this numerator. So the answer is just natural log of inverse sine x. By the way, not a bad idea to differentiate this. Don't worry about the absolute values when you differentiate. Just differentiate log of inverse sine and convince yourself that you get 1 over root 1 minus x squared inverse sine x. The same goes for any indefinite integral. If you ever write down an indefinite integral, you can check your answer by differentiating it and seeing that you get the original integrand back. So those are sort of tricky examples. Here's a more common even type of example that's going to come up next time when we do partial fractions. Again, t equals x squared plus 8 will work just fine. But if you want to use this principle we've been talking about, you notice the derivative of the bottom is 2x. But we don't have a 2. Never mind, we'll just put in a 2. Of course, you can't just go and throw in a 2. You have to compensate with a half. But that's fine. Constants go in and out of the integral sign. And now you can just write down the answer. Half log of x squared plus 8 plus a constant. Anyone tell me why I left out the absolute value signs? X squared plus 8 is always positive. You don't need the absolute value signs. It's not wrong to put them in, but it's more stylish. It's more stylish to leave them out. Just be careful. If you do leave them out, make sure the quantity is always positive. Wouldn't be good in that example. Inverse sign can be negative. But, great. So that is the beginning of what I wanted to say about substitution. Now I'm going to talk about definite integrals and substitutions. So since we're starting a new class, here's the general rule. I erase the blackboard. It takes a few seconds. If you have a question, you can start shouting it out, and I'll have an ear open. But you don't have to if you don't have a question, obviously. All right. Let's take a look at a definite integral. Suppose I take the integral from 0 to the cube root of pi over 2 x squared cosine x cubed dx. There's a definite integral. It's going to require a substitution because, again, we have cosine of nasty thing like x cubed, but its derivative is sitting out there. In fact, you may notice that this is almost the same as an indefinite integral we looked at about 5-10 minutes ago. And this is indeed one way of solving definite integrals with substitution. You forget about the definiteness of it, and you simply solve the indefinite integral first. And just to remind you, I won't dwell on it, we let t equal x cubed, we get dt equals 3x squared dx. We divided by 3, and in t land this thing worked out to be 1/3 cosine of t dt, not dx like I wrote before, and so you get 1/3 sine t plus a constant, and this worked out to be 1/3 sine x cubed plus a constant. And I went through that very quickly, as I said, because I just did that example 10 minutes ago. Now, having done this, we now know an antiderivative, and we could write that this is equal to, then, the antiderivative without the plus c evaluated between 0 and the cube root of pi over 2. That's the fundamental theorem. Second fundamental theorem in a nutshell. If you can find an antiderivative, you just plug in the bounds. Take the difference. So, of course, the cube root of pi over 2 all cubed is just pi over 2. And sine of pi over 2 is 1. Good, yes. You still have to know your trig, I'm afraid. This was true for Math 103, and it's probably even more true for Math 104. So there you go. The answer is 1/3, since sine of 0 is 0. Now, that's one way of doing it. To do a substitution with a definite integral, you could find the indefinite integral first as a separate sort of problem, and then plug in the bounds. But there is another way, and here's how it looks. It sort of uses elements of the other one, but it does not go back to x land. We're going to migrate to t land as a definite integral. I will show you how to do this. We start off as before, and we set up our working. It's going to look like this. T equals x cubed, dt is 3x squared dx, and as we found, we wanted to divide by 3. So this is nothing new. So actually, if we switch the integral to t land, you will get, again, just repeating myself, you get a cosine t times 1/3 dt. Now, here's the deal. It is a major error to write 0 to the cube root of pi over 2. I'm not even going to write it. I feel that bad about it. I'm just making some ghostly markings there. See, the thing is, this is x going from 0 up to the cube root of pi over 2. X and t are very different. See, you also have to migrate the bounds, the endpoints of integration, over to t land. You cannot just change part of it. You have to change all of it. You need to change all this stuff and the dx and the bounds. So how do you do the bounds? All you have to do is write two statements. When x equals 0, t is x cubed, so it's 0 cubed, which is 0. And when x equals the cube root of pi over 2, t is the cube root of pi over 2, all cubed, which is pi over 2. That's all within the working. So we've migrated the bounds. Instead of 0 to the cube root of pi over 2, we go from 0 to pi over 2. So this, correctly, is from 0 to pi over 2. And that is the full migration of the definite integral from x land to t land. Okay, that top bound in this case is critical that that gets changed. And now you can solve this integral in t land, and because it's a definite integral, t is actually just a dummy variable. You don't need to go back to x land. You just get 1/3 sine pi over 2 minus 1/3 sine 0, which, as before, equals 1/3. All right, so if you're looking at it closely, you'll see there's not a huge amount of difference between the two methods. Okay, I prefer, in general, the second method because it saves you a few lines. It saves you from sort of saying, okay, I'm going to do the indefinite thing and go back to x land and then substitute it in. This way, you kind of do it more concisely. So I prefer the second method, but they are both cool. All right. Any other questions? Well, here's the deal. Sometimes it is not entirely clear what you should substitute. And that is part of the interest of the problem. If you take any integral and you make any substitution, you get a different integral. Right? You go from x land to t land, or whatever variable you substitute. Now, the new integral that you have may be easier as it is in all of these, or you may actually have made it harder. And that's just a risk you're going to have to take. There's no algorithm for solving integrals, for sure. A lot of integrals can't be done at all, like integral of e to the x squared, as I said at the beginning. Sometimes you just got to try a few different things. Even if you think your calculator or computer program can solve integrals, it has an algorithm, true. It knows how to try certain things, but it's very, very fast, and it can actually try, sometimes if it's a tricky integral, it'll try 30 different things and before it finds something that works. Or maybe it'll give up. Unfortunately, most of the integrals I seem to try to solve in my professional life as a mathematician, yes, I do solve integrals, or try to. Normally I ask the computer to do it, and normally it can't do it, which means that I certainly can't. So I wish there was some magic formula, but there isn't. There is practice, and there is a knowledge that at least at Princeton, 99% of the integrals that have been asked have been doable. The other 1% we screwed up. Actually, I hope it doesn't even happen 1% of the time, but you never know. Okay. But nevertheless, I thought I'd just show you a few things. One type of integral that does come up is you might have involved in the integral something like the nth root of a linear factor, like this. So, for example, the cube root of x minus 7, or something like that. So the interesting thing here is it's not just a square root. It could be a cube root or some other root. And it's just a linear function there, no squares or something like that. If there's a square in here, we're probably, and this is a square root, we'll do that in a couple of weeks. That's probably a trig substitution. But if there is something like this, then I recommend that you do the following. Just set t equals this, and then try to work it through. Now, the whole thing. Let t be the entire thing. And take nth powers first to solve for x. This will make more sense if I do an example. So here we go. Suppose I want to integrate x times the fifth root of 3x plus 2. Seems a bit messy. Just to clarify, this is not x to the fifth. This is x times the fifth root. Okay, so according to the prescription here, let t be the fifth root of 3x plus 2. Now, I could just differentiate, but I can be snazzier if I follow the extra piece of advice and take the fifth power in this case. So suppose I do that. I get t to the 5 is 3x plus 2. I could actually solve this for x, and I probably will in a few seconds, but I just want to point out that you can differentiate this at this point. This is allowed. Even though it's not just t equals something, it's t to the fifth, you can sort of implicitly differentiate both sides and get the legitimate equation that 5t to the fourth dt is 3 dx. That's true. And so, actually, instead of having an expression for dt that's complicated in x, look at any one of the other examples. I don't know. Let's just take a look at this example. We'll just scroll up here. T is x cubed, dt is something, and you just hope that the 3x squared is there, or x squared is there. But in this case, back down here, we can actually solve for dx very simply, just by dividing by 3. So you actually get 5/3 t to the fourth dt is dx. It's a little bit different. I just want you to contrast that with the fact that we can actually substitute for dx. In fact, let's start migrating this integral over to t-land. The dx piece, which I'll underline like this, is going to be 5/3 t to the fourth dt. How about this? That's just t. But we still got to deal with this. We've got to migrate that factor of x over to t-land. But that's okay. We can take this equation down here and solve for x just by subtracting 2 and dividing by 3. And if you do it, you'll find x is t to the 5 minus 2 divided by 3. So I propose to put that up in here, t to the 5 minus 2 divided by 3. And that's this. You don't have to put those wiggly lines and little dashes. I'm just putting that in for your reference here, so you can see how that each piece of the ingredients in this soup moves over from x-land to t-land. Okay, so what next? We've gotten rid of the roots. Do you have a suggestion or a question? Okay, what's the question?
Second line from the bottom.
Yes.
Did you write this to what? dx to dt? What did you do both sides?
What I did here is differentiate t to the 5 with respect to t. And I get 5t to the 4th dt. And here, I differentiated 3x plus 2 with respect to x, and I got 3 dx. You can do this, and it's again justified by the chain rule. It's justified by the chain rule. In fact, you can see it in this case quite easily that it's correct by differentiating this expression, x equals t to the 5 minus 2 over 3. You're certainly going to get this. Where you cannot do it is if, without being really careful, is if somehow one side has stuff in both t and x. Then you'd have to be differentiating implicitly with product rules, and that would be very, very tricky. But everything is fine. We're basically hitting both sides with a d. It's all justified by the chain rule. But it's just nice how it works out so clearly. If you don't like it, solve fully for x and then calculate dx, and you will indeed get 5t to the 4th over 3. Anyway, we've still got to finish this. Don't panic. It's just, we can first of all pull out 5/9, and it just can be expanded. In fact, the first term will be t to the 5th, a t, and a t to the 4th. So you get t to the 10th. So there's a factor of 5/9 that pops out. We'll have a t to the 10th. And the other factor is just t to the 5th, but there's a 2. Just bookkeeping. Now, when we integrate this, we get t to the 11 over 11 minus 2t to the 6 over 6 plus a constant. There's a tiny, teensy little bit of cancellation here in that we can change this to a 3. Cancel out the 2 and the 6. And so what are we left with? 5/99 t to the 11 minus 5/27 t to the 6 plus a constant. Are we finished? Who thinks we're finished? Who doesn't think we're finished? Who doesn't think? Good. Now, the deal is this. T, we have to go back to x-land, and for this purpose, I'm going to write t actually sneakily as 3x plus 2 to the power 1/5. After all, a fifth root is a 1/5 power, and if I do that, then I can replace this by 5/99 times 3x plus 2 to the 11/5 minus 5/27 3x plus 2 to the 6/5 plus constant. Any questions? Shout them on out if you have. So it's worth practicing these linear powers Some of them can be a little more difficult. That example there, I should just mention, everything over here ended up in the numerator. There was no t stuff down in the denominator. And that is essentially because I just had an x. I didn't really have a denominator in the original. If there were a denominator, then you'd probably have to use partial fractions. And I've seen examples like this. We haven't done partial fractions yet. We'll do it next time. But I just want you to be aware that even this can end up with a new problem that you kind of have to just then work for another 5 minutes to solve. You solve that, and then you have to go back and put t back to x land. So sometimes these things are like a rabbit hole, Alice in Wonderland sort of thing. And it's very good, by the way, to keep tables of working and set out your work very clearly. Right. How about just one more substitution example? E to the x over e to the 2x plus 1. So what are we going to substitute? There's an e to the 2x. There's an e to the x. Which one is which? Who knows? Okay, so the nice thing about e to the 2x is it's the square of e to the x. And so I suggest that you should substitute t equals e to the x. That often works even if you don't think it's going to work. See, you might be tempted to let t be e to the 2x or e to the 2x plus 1. Problem is the derivative would be 2e to the 2x. You've only got an e to the x on the top. So just beware when you have these mixed exponentials. Sometimes the simplest is often the best, which would be e to the x in this case. And again, we have e to the x dx. So the top is just dt. The real trick is to recognize e to the 2x as the square of e to the x. So the bottom is just t squared plus 1. And we hopefully recognize this as inverse tan. Again, we're not quite done. Back to x land by replacing t by e to the x. Again, it doesn't hurt to differentiate if you are doing a final or a midterm or even a quiz, whatever, homework. Just differentiate this as a check. In fact, you could do some other problems, and when you're coming back to check your work, if you have time at the end, don't go through the working again. Differentiate that and see if you get the original back. All right. Again, there are plenty of other things to say about substitution, but they mostly involve doing individual problems. Now, I don't know if anyone here has individual problems. We do, throughout these review sessions, have some time to do it. I know it's sort of being presented somewhat as a lecture thing, and that's partly because of the video, and I want to get through all this material. But if you do bring in problems, then I'm very happy to go through them. You're also welcome to email me, those of you in the room. I can't answer every problem that anyone on the web might want to ask me. Unfortunately, we'll see how it goes. But certainly, if you're taking Math 104 this semester, you can email me. And by the way, since I'm sort of getting you at the beginning of the semester, the route to success in a course like this is to do the homework and get any other problems you can get your hands on and have time and energy to do. But don't be satisfied with saying, oh, I didn't know how to do that. Never mind. Go back and say, why didn't I know how to do that? How should I have thought of how to do it? And how am I going to do it in the future? Then when you come to the final, you'll be really, really prepared. And so, yeah, basically tenacity throughout the semester. That's my advice. Tenacity meaning, don't be satisfied with not knowing how to do something. You can all think of everything in this course. I'm very, very sure of that. I haven't met you all, but I know this is true. A lot of it is, have you seen it before? Did you internalize how to do it? All right. So Again, I will come back and say a little more about substitution in a couple of weeks when I do some sort of summary of integration techniques. I do want to move on to integration by parts now, but are there any other questions that anyone has about substitution? Well, in that case, let's move on to 18.2, integration by parts. All right. We have just reversed the product, the chain rule, rather, when we did substitution. Now let's reverse the product rule. That's the idea. So let's remind ourselves, what is the product rule? Well, if we have two functions of x, variables u and v, which depend on x, then the derivative of the product is the second term v times the derivative of the first plus the first term times the derivative second. So now let's bring this around and make that the subject. Solve for this by subtracting that term, and you're going to get u dv dx is the derivative of uv minus v times du dx. All right, not very exciting. We're supposed to be doing integration, so let's just integrate this. If we do, we get integral of u dv dx. This is a function u. This is another function dv dx. So we're integrating that product with respect to x. And we get the integral of the derivative of uv minus the integral of that with respect to x minus the integral of this other mess, v du dx dx. This term, on the other hand, is quite nice. That's just the integral of a derivative. This is not just the integral of a derivative. It's the integral of a derivative times something else. So you can't simplify that in general. But this one is just uv. And that's basically the formula for integration by parts. But it just turns out there's such a beautiful mnemonic, a shorthand, which is mathematically sound if you interpret things the right way, that sort of involves artificially cancelling out these dx's and these dx's. You're not allowed to cancel them because it's not a fraction. It's a limit of the fraction. Du dx is not du divided by dx. But the chain rule says that you can more or less do this and be justified. So in a sense that I'm going to make precise by means of example with some discussion, I suggest the shorthand notation, which looks like this. More or less the previous formula with the dx's cancelled out. The integral of u dv is equal to u times v minus the integral of v du. That's the formula, almost meaningless by itself, but nevertheless, as I say, I hope to give it some meaning. This is the formula for integration by parts. Again, you start off with some integral, and you get a different integral to solve. It's just like substitution in that sense. However, hopefully the new integral that you get is easier to deal with than the old. All right, so as soon as I've got these boards cleared, we'll look at a whole bunch of examples. Anyone have any questions? Start shouting if you do. Okay. So the first thing I'm going to look at is a fairly sort of standard, straightforward example. looks like this. Integral x e to the x dx. Now, if you just look at this substitution look like it'll work? Is there something that you can see the derivative of that thing floating around? Compare this. If there was a square here, then yes, substitution would be right, because the derivative of x squared would be 2x, and that's almost what we have. But without the square, no substitution seems to appeal. Again, you can try one. It's not going to be pretty. I can't think of anything that's going to make that look better. So let's try integration by parts. After all, if you look at the formula over there, which I'm going to write up again soon, you'll see that the left-hand integral involves a product. So here's a product. So let's call this u. And let's call this dv. Now notice that dv isn't just a function, it also involves the dx. And that's important. You can't have the dv involving just a function. It has to involve the dx. So let's summarize this in a little table. I'm going to say u equals x, and I'm going to say dv is e to the x dx. And the reason I've laid it out like this is because I want to leave a space for du and a space for v. So while we're working on this, how do you get from u to du? You differentiate. So the derivative of x is just dx. But how do you get from dv up to v? You mentally integrate. You normally don't write it there, but I want you to, again, imagine ghostly integral signs over here. The integral of dv is just v. The integral of e to the x dx is just e to the x. And you could put a plus c, but turns out that the c doesn't get you anything. You can try it if you like. Work the entire example through, but where instead of the v is e to the x, try it after we're done with e to the x plus c, and you'll see that the constant just goes away. This is our little template in this admittedly simple example. But I'm going to apply the integration by parts formula as written on the previous board. The integral of u dv is u v minus the integral of v du. And the reason I've written it up there is so that I can write u is x, v is e to the x, minus the integral of v e to the x again, du is just dx. So I've substituted the values of u and v and du. I actually didn't need dv again because it doesn't appear on the right-hand side. So that's a correct equation that comes from the integration by parts formula. If you're going to be really formal about it and not use that abbreviated formula, you'd have to let v dv dx rather be e to the x. So you'd have the dx down here, and you end up just canceling out the dx's anyway. So not a bad idea to try out the original formula and convince yourself that the shorthand works. But basically, I'm always going to be using these du's and dv's from now. Purists, not happy. Practical, happy. All right. We've taken one integral, spat out something, and another integral. What do you think of that other integral? Better or worse than the first? Not bad at all, is it? It's just e to the x. Plus a constant. Don't need the constant in that above line because there's already an integral there. There's already an indefinite integral which has a constant bound up in it. So here is the answer. If you wanted to check it, you use the product rule on this. In fact, we can do it in our heads. Ah, good point, good point. Okay, so the question is, shouldn't I write minus c? No, don't be sorry. It's a fair enough question. Here's the deal. Minus c which could be thought of because there's a minus sign outside of here. That's minus a constant. You can think of that as also plus a different constant. You don't know what the constant is. The constant is indeterminate. So whenever you see minus c or plus 7c or minus 23 pi c squared, you can just replace this by plus c. In fact, my high school teacher always made us write for some constant c to remind us that c is not any particular number, but can actually be any number. And he would take off points if we didn't write for some constant c. I have suitably rebelled and follow the current convention, or the common convention of not bothering to write out for some constant c, but mentally I still think of it. Anyway, the point is, if I differentiate this by the product rule, I get e to the x times the derivative of x plus x times e to the x. And so I actually will have an e to the x floating around as well as the x e to the x. That e to the x will cancel it out, and you'll just get your original x e to the x. Try it for yourselves. Check that the derivative of the right-hand side is x e to the x. Okay, so that's a fairly straightforward example. Now, let me show you a more complicated one. Question? Yes?
The reason you didn't need the C and we can change a dv to v because it gets absorbed by that C at the end. Is that why?
Yes, actually that is why. If you put in, for example, a plus c in this case, what you'll find is, well, it's a little bit more complicated than that. What you'll find is that it more or less cancels out between this term and this term. This is one of the sort of things you'd have to try it for yourself. If you put in, for example, a plus c, you end up integrating c du, which will just be cu. And over here, if you have the plus c, you'll get cu. So this will spit out a cu and subtract the cu, and it really is a case of see you later, as it were. They cancel out. Sorry, that was really bad. Okay, so again, if you try it out, you'll find the plus c's just sort of cancel between the two terms. So that's the one place where you don't really need it. Now, let me give you another example. Let's try this one. Actually, before I do the other example, let's go back to this one. Suppose I had written it out like this. E to the x times x dx. Suppose I gave it to you like that. You might say, oh, well, I'm going to integrate it by parts. Let's let this be u, and let the x dx be dv. Why not? Let's try it and see what happens. I set up my little template. I get u this time is e to the x, and dv is x dx. If I differentiate this, I get du is the derivative of e to the x, which is e to the x dx. And if I integrate this, I get v is the integral of x, which is x squared over 2. And again, I don't need the constant. That's fine. Let's see what happens. We get u v minus the little integral of v du. I'm leaving plenty of space. U is e to the x. V is x squared over 2 minus the integral of v, x squared over 2, times du is e to the x dx. Everything I've written, hopefully, unless I made a silly error, everything that I've written is correct. However, take a look at that new integral that we have to solve. It's over here. What do you think about that? Is it good? How's it compared to the original one? It's worse. Yeah, it sucks. We've made it more difficult. We've taken a power of 1 and we've changed it to a power of 2. And if we were to repeat this, again, letting this be dv, the x squared over 2 dx, and the e to the x be u, you would get a cube power. You can make it as bad as you like by repeating. And if you try to undo it by integrating by parts again on this piece, with this being u and this being dv, you will just undo this and get back to the original integral. Try it and see. So the point is, we've done an integration by parts, but it has been useless. It has hurt us because the new integral we get is worse than the original. So how do you avoid falling in this trap? What did we do wrong here that we did right here? Well, the answer is that when we let dv, that's the really critical thing, be x dx, we're going to increase the power. That just is automatic. Whenever you integrate, you get a higher power. And that's bad. That makes things more complicated in most cases. Not always. Sometimes a miracle occurs and things cancel out. But most of the time, it's not a good idea. Whereas it wasn't a problem with the e to the x, because the integral is no worse. It's just e to the x. Whereas the derivative knocked down the power of x down to just 1. So differentiating polynomials is good. Integrating exponentials doesn't hurt. So basically, so far, what I have to say is, if you have a polynomial, you try to angle that for the u piece. And if you have an exponential, you try to angle that for the dv piece. I didn't write that down, by the way. But it might not be a bad idea for you to take that particular note. What goes for exponentials often goes for trig as well. So here is another example. Suppose you want to do integral of x squared sine x dx. Again, I could have written it as sine x times x squared. So you can't sort of predict which one is u and which one is v. But again, I don't want to let this be dv, because then I'd integrate x squared and get x cubed, which is even worse. Whereas the trig function is not so bad. Okay, so check this out. Let's let u be x squared and dv be sine x dx. So I am partitioning this off as dv and this as u. So du is the derivative 2x. Great, I've knocked down the power. I get 2x dx. The integral of sine x, and you've got to be really careful here, the integral of sine x is negative cosine x. Don't need the constant for integration by parts with the v little part there. So let's see what happens when we do the integration by parts. You get uv minus the integral of v du. That's the formula. U is x squared. V is negative cosine x minus the integral of v, negative cosine x again. Du is 2x dx. Let's just tidy it up a little bit. I get negative x squared cosine x, and the minuses cancel out, and I get plus 2. I'm pulling the constant out as well, and I get the integral of x cosine x dx. All right, again, I started off with an integral, and I get a new integral. But I still don't know how to do it. The question is it better or worse than the original? Well, it's a bit better. I mean, we've changed the sine to a cosine. That's no big deal. Sine and cosine are basically the same. But the important thing is the x squared is now just an x. So we've got to repeat the dose. We're going to integrate by parts again. Now, here is a little matter of technique. You could integrate by parts in place, equals this, equals this, equals this. And every time you'd have to rewrite out the minus x squared cosine x plus 2. The other tactic, which I prefer, is to write this out once and leave a space. And in that space, we're going to write out that new integral when we've worked it out. I'm sort of anticipating that we're going to work it out. And actually, normally, you need one more line to just simplify it. So that's going to be the final answer. I'm going to squeeze it in there. But we still got to do this integral. in order to fill it in. Integral of x cosine x dx. And notice how I'm not bothering with the 2. You could have the 2 there, but it's just messy. It's better to pull these constants out and deal with them later. So how are we going to do this? Same principle. Let u be x and dv be cosine x dx. And this time, although it may not be easy to see, I'm actually using a capital U and a capital V, because in this problem I've already used a little u and a little v, and I feel like you shouldn't reuse variables that you might need again. In this case we won't, but it doesn't cost too much time to put a big U instead of a little u. So here I'm letting big U be x, and I'm letting d big V be cosine x dx. And I'm more or less going to repeat the dose. Du is just dx, and capital V is the integral of cosine x, which is now plus sine x. And I don't need the constant. So I use the integration by parts formula. Big U, big V, minus big V, the big U. Of course, there's nothing special about U and V. You can call it A and B if you like. It doesn't matter. So I get x sine x minus the integral V is sine x, du is dx. And I have now reduced, the new integral is now just the integral of sine x dx, which is negative cosine x. So here's x sine x. The integral is negative cosine x. I'm going to cancel out the minuses and get plus a cosine x. And here I'm going to put the plus c. So that's this integral. Now I'm going to transplant the answer up here and write this as x sine x plus cosine x. Technically, I could put the plus c inside there, and I'd have 2c, but 2c is still a constant. The plus c can go at the end. No problem. And actually, I don't need much simplification anymore. I can just pull out the 2 and get negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. Again, if you really felt motivated, you could differentiate this and see that the original pops out. You should get a lot of things canceling out so that all that's left is x squared sine x. So sometimes you have to integrate by parts twice. Anyone have any questions about that? Shout it out if you do.
You said that the polynomial should be u, and it's an exponential or
Trigonometric
term should be dv.
That is a good rule of thumb. It is not a universal rule. There are always, well, not always, but yes, there are counterexamples to these things. But if I had to say what to do in 9 out of 10 problems, then that would be the case. Yes, I would prefer to let an exponential be dv, because then when you integrate that, it stays as an exponential, doesn't become worse. Whereas when you differentiate a polynomial, it becomes better. Okay, actually, while I'm saying it, I'm not sure I have an example of it on the pipeline. Maybe I do. Log x. If you have a log x and you integrate by parts, write this down. Let that be u. Because integrating log is bad. It's very hard to do. In fact, we'll do it later. But differentiating log is beautiful. When you differentiate a log, you just get a 1 over x. The log goes away. So maybe I will state that again in a different context soon. But I want to show you a different type of example. Integral cosine x e to the 2x dx. Now this example, you've got a trig function and an exponential. So which one's going to be dv? You can't very well let them both be dv, so you were just asking me up the front here, you know, what do you do? Well, exponentials are the least affected by integration. A trig function is okay, but it still flips from cosine to sine. So actually, in this case, I'm going to let the exponential be dv. So somehow, if I had to tell you what I prefer to be from dv down to, from most favorite to least favorite, exponentials, followed by trig, followed by polynomials, followed by logs. General rule of thumb. From favorite to least favorite. So I'm going to let this be dv. I'm going to let that be u. So what do we got? U is cosine x. dv is e to the 2x dx. So du is going to be negative sine x dx. And v, what's the integral of e to the 2x? We can do that in our heads. We don't need a substitution. It's 1/2 e to the 2. Good rule of thumb again, if it's just e to the x, it would be e to the x. So e to the 2x, if it's just a constant multiple, you divide. Same if you were integrating cosine 2x, that would be 1/2 sine 2x. So if you don't believe it, differentiate. You get a 2 popping out by the chain rule. It cancels out. Don't waste time with the substitution when it's something as straightforward as that. Again, I don't need the plus c, so let's just work it through. I get uv minus the integral v u. So u is cosine x. V is 1/2 e to the 2x. Subtract 1/2 e to the 2x times the derivative minus sine x dx. Tidy up phase. 1/2 cosine x e to the 2x plus minus minus becomes a plus. Half, drag that in, drag that out rather. Sine x e to the 2x dx. Well, take a look at the new integral that we get. Is it better or worse than the original integral? It's about the same. Well, I take some heart that we haven't made things worse. So what I'm going to do is just go with it again. Same tactic as the previous example. Let's try integrating by parts again. Let's leave a little gap here. In fact, I'm going to postpone this altogether, that blackboard, and just work on this new integral that we found. Let's just ignore the half and repeat the dose with sine x e to the 2x dx, planning, of course, to solve this and come back and insert it in there. So I get u and I get dv. Well, actually, let me be true to what I said before and call this a capital U. Because, you know, I've already used little u and little v. Okay, so let's see what happens. U is sine x. D capital V is e to the 2x dx. So this time du is cosine x dx, no minus sign needed. And once again, capital V is 1/2 e to the 2x. All right, this is almost the same as what we did before. We've just got some minus things in different positions. Let's see what we get. Same formula for integration by parts. U is sine x. V is 1/2 e to the 2x minus integral of v, 1/2 e to the 2x, du cosine x dx. Just plugging in, really. See what we get. Sine x, 1/2 sine x e to the 2x minus 1/2 integral cosine x e to the 2x dx. Now again, we shouldn't be surprised that what we got looks very similar to the original. Let's surgically insert this up here. Now, unfortunately, I do not happen to be 7 foot tall. If I were, I could just write the answer in there. But I do have X-ray vision. So I can just write the answer looking through the blackboard. Oh, hell, I forget. I don't have X-ray vision. I was just kidding. I know you all believe me, but cosine x e to the 2x dx. That's what it worked out to be. Let's just expand this out. 1/2 cosine x e to the 2x plus 1/4 sine x minus 1/4 integral cosine x e to the 2x dx. Okay, so we pause for breath here. We've integrated by parts twice. I'm now going to push this up so you can see the second part for a second. I mean, just in case you didn't get it down, it hasn't changed. We have a question first. Am I? Ooh, yes. I didn't copy it down because my X-ray vision. I am indeed missing this. Thank you. There is an extra factor of e to the 2x that did not make it down from the bottom board. Thank you for pointing that out. We do have a quarter, though. Yes. Okay, so the question is, we've integrated by parts twice, and we've now gotten our original integral back, which seems a little bit bad, but it's not. Because look at this whole equation. Maybe we can push the camera over. Is the cameraman okay? You doing okay? So take a look right at the top left-hand corner of that board there. We have the integral of cosine x e to the 2x dx. So we've seen that. Now this equals, equals, equals. And now how about that last line there? We can treat this as a big equation. In fact, just for clarity, I'm going to write the original integral out here again, just to remind ourselves what this equals. So we have this thing we're trying to find, and it equals something else with an integral, but it's the same integral that we're trying to find. So the beautiful thing is we can add this over to there. And we end up with 5/4 of it. So I guess the operation is to add 1/4 of the integral cosine x e to the 2x dx to both sides. That's the operation. And we'll end up with 5/4 of it on this side equals this stuff that doesn't involve an integral. There is, however, a certain need to put a plus c now that seems to have come from nowhere. Now, I don't want to get into the philosophy of why you have to, I mean, you know why you have to put the plus c there. There's no integral anymore. In this previous line, there were integrals in both. Actually, because these two integrals come from different places, they kind of have two different constants. So when you subtract that or add 1/4 of this to the other side, you sort of still have this residual different constant from before. That's getting a little bit philosophical. The practical sort of point of view is that here you have an integral on both sides, and you don't need the plus c. But here, you don't have anything on the right-hand side that's an integral, so it's about time to put the plus c. Anyway, the only thing you have to do now is multiply by 4/5 to get the final answer. So you get cosine x e to the 2x dx. 4/5 of times 1/2 works out to be 2/5. And you're going to have 1/5 plus a constant. And here's the complete solution with, again, you've got to make it clear when you set this out, and maybe this is easier on paper than it is on a blackboard, that this is sort of an extra piece of working that gets inserted up into there, and that this is your final answer. Also notice that you cannot solve this problem by going something equals something equals something equals something, because you spit out the original. You have to add that 1/4 of the original on. So at some point you have to break the sequence and do some manipulation. So again, it's possible to have problems where you integrate by parts and the new integral is not worse or better than the original integral. It is the original integral, in this case after doing it twice. And then you add it to both sides, or you know, subtract or whatever. The only time you could possibly be in trouble is if instead of 1/4 up here, you had gotten exactly plus this, and it would have cancelled from both sides. That would be really, really freaky. I don't know what you'd do. Just panic. You probably made a mistake. Because then they would just cancel out. You'd have no integral at all. That would be sort of weird. The only way that would work is if what was left over was actually a constant. So then it would make sense, because you're allowed to have a plus c there. So hopefully that will never happen to you. All right. I have a few more things to say about integration by parts, but then I have some other things to say about trig functions. So as I'm clearing some space, again, questions please, if you have them. I'm all ears. All right. Well, oh, question? No, just a noise. Just a random noise. Okay, so then something else about integration by parts. As you've seen, all the examples have involved products of two functions. But here's an example that doesn't. Just the integral of log x, or any power of log x. This will also work. This does not look like a product. In fact, you might think that you already know the answer to this. Right? It's just 1 over x. No, 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 no. No. The derivative of log x is 1 over x. This is the integral of log x. Okay? Common mistake. This equals 1 over x plus c. As I said, no. Now, how do you do this? It's not a product, but you still integrate it by parts. Watch this. Let this be u, and let this be dv. That's right, dv is just dx, not something dx like it's been in the other examples. Let's see what happens. U is log x, dv is dx. The derivative of log x is 1 over x dx, and the integral, well, v is just x. Don't need the plus c. So there's the working. Let's apply the formula. uv minus the integral of v du. U is log x. V is x. V is x. Du is dx. Something's wrong here. Yes, du is 1 over x. I knew something was wrong, which is why I was staring at the board like a dazed sheep. Now, yes, du is 1 over x dx. So, this is beautiful. This cancels out, and you do just get the 1 that I was hoping that I would have. So this works out to be x log x minus the integral of 1. The integral of 1 is x. And that is the integral of log x. Not commonly remembered. Let's just verify it. If I do the product rule on this, I'll get log x times the derivative of x. So there's my log x. Whereas here I get x times 1 over x. No. Right. It is x times 1 over x. Look, let's just do it. I've stopped being able to think, so I will just write down instead random things and hope that they're correct. This is log x times 1 plus x times 1 over x. So this is just log x plus 1. But the derivative of minus x, which is the other piece, is minus 1. And so that will cancel out with the plus 1. And you will indeed get log x. So there's just a little sanity check, since I seem to be losing my sanity. But hopefully I've got it back, because I'm going to need it as I show you another problem that would use the same technique. It doesn't just apply to logs. This method, by the way, works for log x all squared, or log x all cubed. So these are things to try. Try log x all squared dx. Just let that be u, and let that be dv. I promise you it will work. You'll just have to integrate by parts twice. By the way, as an aside, how would you do integral of log of x squared dx? Anyone have a bright idea of how to do that? Two hands.
Call the log x squared dv and the other one g.
I would say you would want this to be u, if anything, and that be dv, but there's an even cleverer, sneakier way that you can do this. Anyone think of the sneaky way? Yep. Put the 2 out the front. Use the log rules. And we've just done that. In fact, it'll be 2x log x minus 2x plus a constant. So that's kind of nice. That doesn't work for this. That's log x all squared. Anyway, I'm still in the middle of a sentence from before. And that was, it doesn't just work for log x and powers of log, it also works for inverse trig functions. So remember what I was saying before about what you'd least like to be dv and you'd most like to be u? U equals log x was good. I don't want that to be dv, because when you differentiate log, you just get rid of the log. Same goes for inverse trig functions. If you differentiate them, they go away, which is good, because they suck. So consider this. What do I want to do? It's a definite integral. I just forget the bounds I want to do. How about 0 to 1? I should remember that. Let's work out the integral from 0 to 1 inverse tan x dx. All right. Let's integrate this by parts. You know, in my book, if you're reading along, no one in the room is yet, because it's not quite out yet. Next week it's coming out. But the point is, I said that you should not use definite, if you're doing a definite integral with parts, you should not substitute in the bounds. You should just do it as an indefinite integral first, then plug in the bounds. Now that I'm thinking about it, I was sort of on crack when I wrote that. I don't know. I wasn't really thinking straight. So the point is that, yes, I think there's no reason why you shouldn't do it directly. So to atone for this, I'm going to just try to do it like this. So look, I have here u, and I have here dv. It's the same tactic, even though it's not a product. I want the u to be the inverse tan. So watch this. U is inverse tan x. dv is dx. By the way, if the problem was x inverse tan x dx, I would still let u be the inverse tan, and I'd let the dv be the x dx. So again, polynomials, I don't like to be the dv very often, but inverse tan is even worse. So du gets rid of the inverse tan and gives us the integral of 1 over x squared dx, whereas the v just becomes x. So what do I have? I have I have uv minus the integral of v du. U is inverse tan x, and v is x. And because it's a definite integral, I have to evaluate it between 0 and 1. That's what I was avoiding in the book. I don't know why. I really don't remember what was going through my head, but it's a long book. That's my only excuse. And then this is going to be the definite integral from 0 to 1. V is x, and du is dx over 1 plus x squared. All right, let's start working this out. When I plug in 1, I get inverse tan 1 times 1. And when I plug in 0, I get 0 times inverse tan 0, which is 0. And this integral looks like x over 1 plus x squared dx. Now, you may remember from before that I did an example almost just like this. I said, oh, look, the derivative of the bottom is 2x. So I just put in the 2 and the 1/2. Who knows what inverse tan of 1 is? Tan of what is 1? Pi over 4. Of course, there are other solutions, but that's the only one within the acceptable range. How about this? Derivative of the bottom is the top. The answer is just log of the bottom. No absolute values needed in this case because 1 plus x squared is positive. And because it's a definite integral, I'm going to evaluate from 0 to 1. So I get pi over 4 minus 1/2 log of 1 plus 1 squared is 2, and 1 plus 0 squared is 1. Log of 1 is 0, so this will just be pi over 4 minus 1/2 log 2. Of course, you could do what I suggested in the book, which is ignore the 0 to 1, work out the indefinite integral first, and then substitute. But there's the alternative. So it wasn't bad advice, it just was unnecessary advice. Okay, well, again, you've got to try lots of these integration by parts for yourself. You will find it's nothing more than applying the formula, but only after you've made the correct choice of the u and the dv. And that's really where the tricky part lies in most cases. Any questions about integration by parts? Yeah. Is it a specific question about one of these examples before? Okay. Okay, let's look back over here. So before I even used log rules, I just plugged in 1 and I got log 2. And then log 1. The only log rule I use is that log of 1 is 0. Okay. However, in this sneaky example over here, I did use a log rule as well. Log of x squared is 2 log x. Those are the only log rules that I've used. But you should go back and look over your log rules. They come in very handy. Okay, any other questions about integration by parts? Yeah.
The 2x over 1 plus x squared.
Yes.
How does that turn the ln of 1 plus x squared? Wouldn't it have to be just dx over 1 plus x squared?
So looking over here, the question is, how did I do this? And I did it earlier. I don't know if you were in the room. Basically, I discussed the principle that if the derivative of the bottom is just sitting there on the top, the answer is just the log of the bottom. And the reason it works is because of a substitution. But it comes up so often that it becomes a rule. So think about differentiating log of 1 plus x squared. What would happen? Well, it's log of something, so you get 1 over 1 plus x squared. But then, because it's not just log of x, you have to multiply by the derivative, which in this case is 2x. Right? So that's a good rule of thumb to know. Notice how in the original I just had x, but I wanted it to be 2x. So I cleverly, I mean, I've seen it before, so it wasn't really clever of me. It's a nice little labor-saving trick is to throw in the 2 and the half.
So did you have to do it the way you did where you changed the bounds, or could you still do it the other way and then as an indefinite integral and then at the end?
Yeah, as I was saying, and as I said in my book, you could ignore the 0 to 1, do the entire integral as an indefinite integral, get the answer with a plus c, and then put in the bounds without the plus c, and you should get the same answer. Okay? Any other questions? We have about 25 minutes left, and here's how I propose to spend it. I would like to skip ahead in my book, as it were, to chapter 19. The rest of chapter 18 in the book is partial fractions, and that's the subject of next week's class. However, in chapter 19, there's some stuff about integrals involving trig functions. Now, a lot of this is going to be used in trig substitutions, which is what we're doing 2 classes from now. But there's not really any time to do it. And it's not really written down anywhere. And you're just sort of supposed to know it. How are you supposed to know it? I don't know. So I'm going to show you now. All right? So I'd like to spend a little bit of time. And I may not finish this, but I hope that I've finished some of it. What I don't finish, I will do in 2 weeks' time, with a bit of a reminder of what we found this time. So this is sort of a mixed bag of trig-type integrals, some of which involve substitutions. First of all, let's look at some integrals that involve trig identities. Do these count as substitutions? I don't know. They're just integrals. But here are some really useful identities which you absolutely must know. I'm going to write them out like on top of each other like this. So this says cosine squared x is 1/2 of 1 plus cosine 2x, and sine squared x is 1/2 1 minus cosine 2x. Where do these come from? Well, it just comes from the cosine 2x identity. It's just a rearrangement of this common identity. Cosine 2x is 2 cosine squared x minus 1. If you take that identity and just solve for cosine squared 2x, you get this. So I'm going to put this big box around them because they come up in this form all the time when you integrate. Very common. So you absolutely need to know those. And I write them in this form because you can see they're very related. In fact, if you add them up, on the left-hand side you get cosine squared plus sine squared, which is 1. On the right-hand side you get 1/2 plus 1/2, which is 1. And these things cancel out. So if you know one, you clearly get the other. Okay, now, here's an example of where you would use such a thing. So suppose I ask integral from 0 to pi over 2 square root, make sure I get this right, 1 minus cosine 2x dx. Well, it doesn't look like any substitution's going to work. Substitution would be great if there was a sine 2x floating right here. But there isn't. Sine 2x, of course, being related to the derivative of cosine 2x. Integration by parts, I don't know, you could try letting this be u and that be dv or something. But it seems pretty nasty. Then you'd have to differentiate this. Right? When you do integration by parts, you differentiate the u piece. I don't want to differentiate the square root of 1 minus cosine 2x. So let's use the trig identity. In fact, if you stare at this second identity, you see it's actually just integral from 0 to pi over 2 square root 2 sine squared x. Not 2x, just x. That's the double angle formula. Well, root 2 is just a constant, so I'll pull that out. And the square root of sine squared x is just sine x. Oh, I feel very bad about saying that because, you know, you've got to be really careful when you take the square root of something. You need absolute values there if you're going to do this properly. The square root of x squared is just the absolute value of x. It's true for anything. Square root of a square is the absolute value. Now, as it happens, between 0 and pi over 2, sine x is positive, so we can write this as root 2 sine x dx. And this is a very simple integral that I'll leave it to you. Works out the integral there is just 1, so the answer is root 2. Okay? It wouldn't be wrong if you left out the absolute values, because as you see, you don't need them. But that would just be lucky. Consider instead this example. Integral from pi to pi of 1 plus cosine x dx. How do you do this? Again, no substitution seems to appeal. Integration by parts doesn't appeal. Let's use the top of these identities. Maybe we can just look at that. Problem is we don't have 1 plus cosine 2x. We have 1 plus cosine x. Well, no matter. Just mentally replace the 2x by an x. And so this would mean, down here, that you have the square root of 2 cosine squared x over 2 dx. See, you got to use the above identity, but instead of x, you have to change x to x over 2, and you will get the correct answer. So let's continue. We'll pull out the root 2, and now we know better than just to put cosine x over 2. We're putting the absolute value of cosine x over 2. Integrals involving absolute values are nasty. They're mean and messy. They involve splitting up, as we discussed at the end of Math 103. If you're watching online, that was just the last lecture and the one before it. We discussed how to deal with absolute values. Basically, the only real way to do it is to graph the function and see if it's above or below. And if it's both, you have to split up the integral. Now, this is not so bad, because if you draw the graph of cosine x, looks like this. Actually, the graph of cosine x over 2, if you think about it, we're going x from pi to 2 pi, so x over 2 actually goes from pi over 2 up to pi. So all you have to do is relabel the axis. Instead of pi over 2, I label it pi, 2 pi, 3 pi, 4 pi. So if you think about it, that's a graph of y equals cosine x over 2. It's just sort of the same as cosine, but it's kind of half as fast. It takes a long time before getting up to pi. I didn't draw this to scale, obviously. Pi is about 3, and that's 1. But in any case, we can see that between pi and 2 pi, this graph is below the axis. And so this is a negative quantity. So you need to put a minus sign when you take the absolute value. How's that for mean? But it's fair game. I've seen problems just like this on Math 104 exams. How do you integrate cosine x over 2? Well, if it was cosine 3x, you divide by the 3. So now we divide by a half. You could do it by a substitution, but I'm just going to effectively divide by a half. So you get multiply by 2. Integral of cosine is sine. And then finally, evaluate that between pi and 2 pi. So there's a lot of ingredients going on here. Just double check this. If you differentiate sine x over 2, you get cosine x over 2 times 1/2. That 1/2 kills off this 2. And the minus sign is because of the absolute values. So lots of stuff going on here. Anyway, if you work this out, you get negative 2 root 2 outside of sine pi minus sine pi over 2. Sine of pi is 0. sine of any multiple of pi is 0, whereas sine pi over 2 is 1. So this becomes minus 1 times minus 2 root 2, and we finally get 2 root 2. Nasty. I want to point out something. If you forget the absolute values, and you just say, oh, square root of cosine squared is just cosine, you will get a negative answer, minus 2 root 2. And if you look at the original problem, that cannot be right. This is a positive quantity here. Square root 1 plus cosine x. Square roots are positive. So this integral is of a positive function. It has to be a positive answer. Danger bells, warning signs, whatever, should go off in your mind if you get a negative answer to this problem. Just when you're checking it, you say, whoa, positive function, negative integral? No. The only way that could possibly happen is if these were reversed. If it went from 2 pi to pi, where 2 pi is bigger than pi, then yes, you get a negative answer. But that's sort of weird. Anyway, so the mistake would have been that you didn't get the absolute values right. And that is a definite technical wrinkle that you have to worry about. Any other questions about that example? Yeah?
Could you explain one more time why it's negative 2 times square root of 2, not negative 1/2 times square root of 2?
Okay. The question is, why do I have a 2 there instead of a 1/2? So just look at these integrals here. What's the integral of cosine 2x? I claim that the answer is 1/2 sine 2x plus c. Do you believe it? Differentiate this. Sine 2x. 2 pops out and kills that. I claim, on the other hand, that the integral of cosine x over 2 is 2 sine x over 2. Again, differentiate this. This time the 1/2 pops out and kills the 2. Right? So the general rule of thumb is you divide by when you're integrating, you divide by whatever is here. And here I have a 1/2, and dividing by a half is the same as multiplying by 2. All right? Okay, so here's what I propose to do. I actually propose to only do one more question, which is sort of long and involved, but rather than go and embark on all the powers of trig functions that I thought I might have time to do, I will just play it more gentle. We've already looked at a lot of stuff, and we've gone a little far ahead, in fact, for those of you in the room. Become more of a preview session than a review session, but, you know, fair enough. But I want to look at one more example, as I said, and I'll have plenty of time to do the rest of the stuff. So, here is a pretty nasty example that I do believe I saw in a Math 104 final problem sheet about 10 years ago. Here it is. Or else I saw something similar. One over the integral of secant x minus 1. Again, no substitution looks appealing. Integration by parts doesn't look particularly good. So, I propose to use a trig identity that is not one of the ones in the box, but instead comes from the 2 or 3 Pythagorean identities that you should know. Here they are, just for reference. Cosine squared plus sine squared is 1. You've also got 1 plus tan squared x equals secant squared x. And you have cotangent squared x plus 1 is cosecant squared x. I wrote them in a somewhat eccentric manner. Actually, if you take this one and divide by cosine squared, you get this one. But if you took the original and divided by sine squared, you get this one. That explains the order that I wrote these things in. Anyway, these are essential. Question?
Why
Why can you not make it cosine x minus 1? Well, here's the answer. If you were going to do this, you'd have to write it like this.
Could you split it? Or, I mean, could you split that and do?
Not allowed to split a denominator. Can only split numerators. 1 over a plus b is not 1 over a plus 1 over b. Sad but true. Life would be very easy from a point of view of solving math problems if it were. Unfortunately, we probably wouldn't exist if it actually were.
Same as doing 1 over sec x minus 1 over 1.
Nope. Again, 1 over a minus b is not the same thing as 1 over a minus 1 over b. If it were, the laws of physics wouldn't work, and I wouldn't be telling you that. That's pretty much true. I don't want to get into mysticism, but unfortunately, that doesn't work. It only works, you can only split up a fraction if the numerator is in 2 pieces. Just algebra. Now, back to this problem. The middle identity might give you an idea. If you rearrange this, you get secant squared x minus 1 equals tan squared x. So let's multiply by the conjugate of the bottom. Multiply and divide. It's a nasty little trick, this. Multiply by secant x plus 1 over secant x plus 1. And you will get secant x plus 1 over secant squared x minus 1. Now, according to this middle identity here, slightly rearranged, secant squared x minus 1 is tan squared x. So the bottom becomes significantly simplified if you write it as secant x minus 1 over tan squared x. All right. Now, I propose to split this up, which is now fine because it's the numerator. I'm just going to split this up into 2 integrals. The first is secant x over tan squared x. And the second is 1 over tan squared x. Again, this is fine because it's the numerator that I'm splitting up. I have the same denominator in both places. Now, in order to deal with this, I've got to deal with 2 integrals separately. Yes, thank you. Okay, let's just scroll back. I've made a mistake. Plus, plus, plus. Of course, I was just trying to keep you on your toes this time. I knew about this all along. Okay, never mind. I didn't know about it. Easy to make mistakes. Thank you for being diligent in correcting my inanity here. I am going to leave this space and solve these 2 integrals, hopefully without making too many more mistakes. I get secant x over tan squared x. Let's do that one first, because it's the harder one. I don't see any really appealing substitution. My gut feeling would be tan x, but the derivative of tan x is secant squared x. So if this was secant squared here, I would consider tan. It doesn't work. So I don't see anything really nice. So I'm going to resort to switching everything to sines and cosines. That's another sort of way to handle these things. So if I do that, I get 1 over cosine x divided by sine squared x over cosine squared x. And now at least I'll have a little bit of cancellation. In fact, if I bring this cosine squared all the way up, I will find I only get 1 cosine x over sine squared x. Now, there is an appealing substitution. Now there's an appealing substitution. Let t equal sine x. dt is cosine x dx. And this will work. And I want you to finish it and see if you can get the same answer as what I'm about to get by doing something really tricky. Watch this. Instead of doing the substitution, I'm going to write this as cosine x over sine x, and another sine x is here. So this works, but is not the only way. In fact, if I split the bottom like this is just a cotangent, and that's a cosecant, and the derivative of cosecant x is just negative cosecant cotangent. So this I recognize as the negative of the derivative of cosecant x. And how about that? A miracle. Again, if you do the substitution, you should get negative 1 over over sine x, which is the same thing. So this is a really sneaky trick. Could you tell that secant x over tan squared x is the same as cotangent x times cosecant x? I couldn't. But it's true. And that's an integral that's on the table. And that's just a standard integral. Actually, the other piece that we still have to do is 1 over tan squared x, which I'm going to write as cotangent squared x. And this is another standard integral. Anyone remember that integral? What's a function whose derivative is cotangent squared? What's the integral of tan squared x? Actually, you know what? There's no nice thing here, is there? I'm just leading you up the garden path. There's one other thing we have to do first. I'm getting ahead of myself. There it is. One more trig identity to deal with. I'm going to write this as cosecant squared x minus 1 dx. I told you this was long. Okay. Now I ask again. Is there a function whose derivative is cosecant squared that we know off the top of my head? That one, the answer is yes. Suppose this was secant squared x. What would the answer be? Tan, right? The derivative of tan is secant squared. The derivative of tan x is secant squared x. The derivative of cotan x is negative cosecant squared. So the integral of this is negative cotan x, and then minus x from this from this 1 here. Great. These are different constants, but we've done both our integrals, and they all have negative signs in front. So if I take this plus this and write it up here, I will get negative cosecant x from this one, and then negative cotangent x from this one, minus x. And then just a big plus c at the end. And that, my friends, is about as nasty an integral of this type as I could imagine. You have to do a nasty trick at the beginning of multiplying, use a trig identity, bust it up into 2 pieces. Each piece involves messiness. But there you have it. Next week, integration by parts. See you then.